on. Hello, this is Jeff, and I'm Charles, and we're part of the Big Data Platform Architecture team at Netflix. And today we like to talk about some of the types of tools we're creating to make it easier to work with our data. Like a lot of other companies, we're experiencing an explosion of data at Netflix, and we're a data-driven company, and that's a really good thing for the most part. But what we're finding is, as it becomes harder to find the data in that large data, or it's harder to process, longer to process, a lot of times the value of our data is diminished. And that makes sense, right? If you're spending more time, processing the data that you had before, or when you have a new idea, it's harder to find the data that you're looking for, or you don't have the resources, the people to do it. You just really can't innovate, and we can't develop new things for our customers as fast. So our goal as a team is really to make the data as easily accessible, easy to process as possible, so that anyone at Netflix can do new and interesting things.
So before we start talking about the architecture that we're developing, it's important to understand the users that we're developing it for. Netflix loves to hire really smart people, and those people that we hire aren't afraid to get their hands dirty with the data. So we like to think of our users as existing on a sort of spectrum, where on one end we have analysts, and the analysts really understand the data really well, some facet of the company, and what they want from us is a rich set of tools that they can use to get at the data easily without any roadblocks, and just get the data that they need without really worrying about the technology underneath. On the other end of that spectrum, we have our engineers who are working on innovating some portion of the product, and what they want from us is a really rich API layer that they can plug into so that they can integrate the data with the application that they're developing somewhere else in our architecture. So one thing that all of these users have in common is that they're really self-sufficient, and they don't want us to be roadblocks into them doing their job. And we certainly don't want to be gatekeepers of the data. So as we're building out services and tools in our architecture, the concept of self-service is something that is pervasive across everything that we're building. So the architecture of Netflix is a highly decoupled service-oriented architecture, and our Hadoop platform is no different. So certainly, Hadoop platform as a service isn't something that's unique to Netflix, but our flavor of it does have some things that distinguish it from others. And so central to our platform is the fact that we've chosen S3 as the source of truth for all of our data. And so what that does for us is it allows us to decouple our storage from our processing of the data. And so we exploit that fact by running multiple Hadoop clusters against the same data sets. And so you might think, running multiple Hadoop clusters against the data could cause confusion for our users. And so what we've built is our Hadoop platform as a service layer. It's called Genie. And that abstracts the infrastructure that we've built on the back end from the users on the front end into a RESTful interface that they can use to submit Hadoop, Hive, and Pig jobs. So I'm not going to talk too much about that Hadoop platform as a service layer. That was the talk that was given yesterday by one of our colleagues. And so what we really want to talk about today are the services and tools that we're building on top of that Hadoop platform to really unlock the data, make it more accessible and easier and more efficient to use for the people that are developing on top of that platform. And so rather than talk about Hadoop platform as a service, we want to talk about the things that we're building on top of that we call our data platform as a service. And so this is a picture of what that looks like at Netflix. And you can see at the bottom there we have our data that we're processing on Hadoop stored in S3. Most of the processing that we're doing on it is with Hadoop, but we're also using some other technologies as well. And so on top of that, in the black, is the layer of services that we call our primitive services. And so Genie is one of those, our Hadoop platform as a service. But there's also Franklin, which is our metadata API, and an orchestration service that keeps track of workflows running on our architecture that we call our event service. So on top of that, we have built on the more primitive APIs and services that we're building, some higher level tools. And we want to deep dive in a couple of those tools today. So we're going to talk a little bit more about Lipstick, which is our Pig workflow visualization tool, and Sting, which we use for fast in-memory aggregation and visualization of data in our architecture.
So Jeff and I really fall on the engineering side of that spectrum, and as such, the technology that goes into our tools is really interesting to us. But most of our users, they really don't care how our services scale. They don't care what kind of code and languages we're writing in. Really, the tools are only useful to them in how that it allows them to more easily utilize the data, which really makes sense. So we thought when talking about our architecture, it makes a lot more sense to look at it from the perspective of our users who are just trying to do something interesting with the data. So we're going to have a little mini hack day today, and what we thought we would do is build a recommender. So Netflix is doing a lot of cool, interesting things with our data right now, but at the end of the day, we're really about connecting our customers with great content. And one of the most visible ways that we do that is recommending content to you. So we thought this would be fun. And so let me really quickly talk about how we're going to build a recommender. So there's two types of recommendations that you really get at Netflix. The first is based on similarity. You've watched a movie, here's several other things that are similar to it. And at a high level, you can really just think about that as a distance. If you could take one movie and measure the distance to all the other movies, things that were closer you'd say are more similar. So we'd really like some way of measuring distance between movies. And personalization, means a lot of different things. We do a lot of things that are personalized to you. But again, what we want to do for personalization in a recommender is say, given what we know about the user, what can we recommend to them personally? So when you come to the web page, what are the things that are personal to you? And again, it would be really nice if we could just take each customer that we have and measure the distance to all the movies and say, now, we're between movies, that was similarity. Now, if we can measure between a customer and the movies, that'll be our personalization, what they're going to like. So the closer they are, we want our recommender to say, here's the 5 things that are closest to you. So what we need to do is come up with a vector space in which we can first measure distance between movies, and then we're going to project our customers up into that vector space and then measure the distance between users, customers, and movies. So that's the basic idea. And today, we thought we would do colors. Colors are really simple. We can visually explain it. It's quick to understand. And so what we're going to do is take our box art. So today, we're going to say that 2 movies are similar. If 2 box arts have very similar colors, the closer they're going to be together. So we're going to try to use that as our distance of measure. Now, some of you read our abstract and are thinking, Netflix does really cool recommendation algorithms. You probably have a lot more interesting things than that. And that's true. We can definitely do, we're doing a lot more with our data than that. But the point is, our platform is to be available for any idea. When someone at Netflix decides that they want to go and figure out a correlation between box art colors and viewing history, they should be easily able to find that data, do the work on it and the processing. And sometimes, those are really great ideas. Sometimes they're crazy ideas that don't pan out. But the platform should be available for all of that. So with that out of the way, for a user, the first thing that really comes up when you're trying to explore a new problem is, you're logging all kinds of data. Where the heck can I find the data that I need for this process? So where in the world can I find this color data?
So I mentioned a minute ago that the source of truth for the data that we're processing on our Hadoop clusters is S3. And so the problem with S3 is that it's a really big place. And for Netflix, we're storing petabytes of data on S3 that constitute thousands of data sets that our users might be interested in processing. And to make matters worse, we have data in a variety of other data sources as well. So we've got data stored in Teradata, Redshift, Cassandra, MySQL, and frankly, more data sources than I could fit on this slide. So to solve this problem for the users, we've built a metadata API layer to sit on top of that we've named Franklin. And so from the user's perspective, Franklin is both a technical and business level data dictionary into our data. And what it does is it exposes a nice homogeneous API that can allow you to search into all of these data sources to find data that you're interested in, understand the schema, the format that it's stored in, and basically know how to deal with getting at the data. From an engineer's perspective, what Franklin is a nice API that they can hook into when they're trying to write loaders and stores for this data, be it loaders that are loading data into a machine somewhere in our AWS architecture, or even loaders that can copy down or store back up data from a developer's hard drive. Now, from the Hadoop perspective, whenever we write a loader or store into data in our architecture, Franklin is the entry point for all of that stuff. So rather than think about data being stored into S3 or MySQL or Redshift or whatever, we think about data being stored at the Franklin layer.
So maybe not surprisingly, but really disappointingly when I started to do this, nobody had actually created a data set in anywhere with colors, box arts and colors. I mean, it was really sad, but so and I'll explain that really quickly. Box arts media, we don't put it into our big data, just like we don't put the movie data. So the first thing I needed to do was create a data set in Franklin that I could use for this kind of analysis. And what I did have in Franklin was, a list of titles. I downloaded, used the IDs to download all the box art. And so what I did there was I used ImageMagick to convert the box art into web-safe colors. This gave me a 216 dimensional vector that I could use. And the reason for this was just purely, the box art has a lot of different pixels, and some of them are red, and some are slightly different red. We really want to be in a space where we can measure distance between, and we don't want those reds to be different. So I created that data set. I put it back into S3, made it available in Franklin so I could do additional analysis on it. And that brought me to the next thing that a lot of our users want to do, and that is really, I wanted to visualize this. Now I could create graphs myself, but really what I want to do is, give someone else the ability to, I want to share the data with other people, explain to them what I'm doing, and let them slice and dice through the data so that they can really get an idea of what I'm doing and give me feedback on whether or not it makes sense.
So, certainly we have some pretty industrial strength tools at Netflix that we can use for reporting on our data. We've got MicroStrategy, we have Tableau, but it turns out that there was a huge appetite around the company for a quick and simple way to visualize data that was well integrated into our Hadoop infrastructure. And so we created Sting, which is our fast in-memory aggregation and visualization tool. And what Sting does is it allows users to specify a job that's going to run on Genie, and it caches the data set that comes out of the result of that job. So you can think of the data set from that job as being a base level aggregate that we can serve fast sub-second responses to OLAP-style operations on top of. So we allow for slicing, dicing, and reaggregation of the data that's coming out of basically any kind of Hadoop job. And we have a nice JavaScript visualization layer on top of that. So the key thing about Sting that's led to its adoption around Netflix is that it's just really simple to use. And so this is what that kind of front end looks like to be able to specify a new data set into Sting. And so it's really as simple as creating a Hive query, pasting it into the box there, and telling the system what the schema is going to be that comes out of that Hive query, right? So it takes about 5 minutes to set up. User clicks on Save Dataset. We submit that query through Genie, and once it finishes running, we get the front end that's available for Sting that users can use to do that kind of OLAP-style operations on, embed into wiki pages, mail around the company. So basically share and explore the data that comes out of that result. And so I'll just really quickly walk through some of the features of the UI here. You can see here that we're charting the % content consumed per hour for a couple days of viewing on Netflix. And over on the left here, I can filter and slice and dice and change the aggregation that I'm doing. Right now, it's displaying it as a simple time series. and I'm summing up the view hours. So we support lots of different kinds of aggregation. Over on the left, there's a drop-down box. It's on sum right now. And we can see we're filtering it for drama and children and family content. So I won't talk too much about what we're seeing in the graph here, but one thing becomes pretty obvious. It's that children who are watching children and family content versus adults who are watching drama are obviously going to bed before adults. You can see that the viewing curve for the children and family content starts to drop off a couple hours earlier than the adults. And being able to visualize that data makes those sorts of insights really obvious.
So this is what my data set looks like in Sting. What I've done here is I've grouped on color, and I've filtered for a few titles. So each bar there are the number of pixels in my box art, and the height of each color in there is the count of the pixels in the box art that are that web-safe color. So you can see that Hemlock Grove is about 40 to 50% black. It's got some red in there, various grays. House of Cards black and grays, and Arrested Development's a lot of orange. And looking at this, I'm not really excited about the data. I wasn't really excited. I was comparing titles. I don't really like that the oranges are still slightly different, but maybe that's all right, and grays are different. So I was happy enough with this. I did several different things. I was happy enough with this to just do a simple distance calculation. So now I have this 216-degree vector, or dimensional vector, and just do a straight distance between them. And so this is my similarity measure now, and let's look at how that worked out. So here, I don't know how well you can see this, but this is House of Cards. There's black around the edges. There's gray, like I was saying. There's red, white, blue on the flag. You might not be able to see this, but Kevin Spacey actually has blood in his hands, and here's its top sim by color. Macbeth, black around the edges, gray. Patrick Stewart has blood on his hands. And if you consume both these content, you're thinking these are so close together that you're probably cheating, which we'll go back and look at Sting. And just by comparing these titles again, you can see visually they look very similar. So you get an insight into what your algorithm is doing. It's pretty easy to see that these should be close together. So let's do one more. My algorithm's doing pretty well. Let's do one more to make sure. So this is Star Trek Voyager, one of the more polarizing Star Treks. Purple, black, blues, reds, and this is its top sim by color. So my algorithm's working perfectly. If you look back in Sting, you can see color-wise it's not as great, but obviously we didn't have something that, they're still pretty close together, a lot of purples. So I'm pretty happy with, now how how I'm calculating similarity. Now what I said before is I want to project my customers into this space and measure distance between them. So how I'm going to do that is for each customer, I'm going to take the last n days of their viewing history, and all the titles they've watched during that time, I will add together, I will average the colors. So for each customer now, I will have a 216-degree vector, which is the average colors of titles that they've watched in the last n days. And then once I have that for each customer, I'm going to calculate the distance to all the titles in the catalog.
So what Charles is proposing to do here is to potentially take the number of subscribers to the Netflix service and multiply them by the number of titles in our catalog. And so the result there is certainly going to be of a size that we consider big data at Netflix, and it's something that we're going to want to employ the full power of our Hadoop clusters in order to compute efficiently. So at Netflix, we use a lot of Hive and Pig. And kind of the way we have the two technologies positioned is that Hive is used heavily for ad hoc analysis and kind of preliminary investigation into data. And Pig is used for productionizing workflows that we're going to need to maintain for a long period of time that will hopefully run without a lot of heavy maintenance. So Charles probably wrote quite a few Hive queries in initially developing this algorithm, trying to figure out how data join together, maybe doing some lightweight aggregation, looking at the results. But when it came time to write his recommendation engine, he probably used Apache Pig. And so this is an example of what a typical Pig script looks like in our environment. And it's blurred out on purpose so that you can't actually read it. But you can tell by the syntax highlighting that there's a lot of reserved words in there. There's quite a bit going on. It's a pretty complicated script. And it honestly is just a random sample of one of the data manipulation workflows that go on in our environment. And what's typical of these workflows is that they do grow to this level of complexity pretty quickly. They compile down from anywhere between 10 to 25 MapReduce jobs. And while we've been pretty happy with our choice of Pig for our ETL and data manipulation, once scripts do reach this level of complexity, it becomes pretty difficult to logically tell how data is flowing through this data flow. And it certainly becomes really difficult to determine how those various logical operations that are happening in the data flow are going to compile into MapReduce jobs. So to address that problem, we've built a tool into our environment that we call Lipstick. And so Lipstick piggybacks on top of all of the Pig jobs that are submitted through our environment, be they through Genie or just from the command line CLI. So somebody working in the grunt shell who submits a job to the cluster also will get Lipstick on top of it. And so what Lipstick provides is a visual representation of the logical query plan that a Pig script represents. So being able to visually see the workflow that's going through a Pig script allows our users to really quickly see common errors with their logic. It allows them to easily monitor jobs as they run in our production environment to see how that lineage of MapReduce jobs maps together at a logical level. And really, what we're trying to do with this tool is empower users to be able to support themselves rather than every problem they hit becoming something that the infrastructure team needs to be involved in to help fix. But when the user can't figure out the answer to a problem, rather than what was happening before we built Lipstick, where a user would just kind of email one line of an error that comes from a stack trace to us, or say, hey, my job failed, not even tell us what job it was. Now we've trained our users pretty well to just provide us a Lipstick link, and that gives us as an infrastructure team all the information we need to help them out. So this is a look at what the first bit of interaction any user has with Lipstick in our environment. And this is just standard out for a Pig script that's running. And what we do is we print out a link to the Lipstick UI in that standard out. And so when a user follows that link, they get this. And I'll just explain briefly some of the major features of Lipstick UI. So over on the right, we have an overview of the overall job progress for the Pig script. So we can see when it started, if it ended, when it ended, and the last time it heartbeat progress back to our Lipstick server. Underneath that, we can see the number of MapReduce jobs and their status that this Pig script compiled down into. And so what we're looking at here is actually the color recommendation script that's computing this personalization that Charles was talking about. And we can see, this is actually a pretty simple script. It's compiled down to 5 MapReduce jobs. And we can see what those jobs are doing in a little more detail over on the left-hand side of the UI. So this is probably the most visually interesting portion of the UI. So we'll zoom into that to get a better idea of what's going on. The light blue bounding boxes represent MapReduce jobs that the script compiled down into. And each MapReduce job contains a series of logical operations. And so those logical operations have pretty much a one-to-one correspondence with statements in a Pig script. And so you can see from the headers on those logical operators, they're things like load, store, filter, group by, for each, right? And if you've written a lot of Pig, you can tell that those are the same kind of statements you're writing in Pig. So underneath that in the dark gray, we print what Pig alias is responsible for that logical operator that's being graphed. And underneath that, kind of in the white boxes, we show information that's pertinent to whatever that logical operation is. So for example, if you're doing a for each statement, you're probably transforming the data somehow. So we're showing the schema and how it changes in that transformation. If you're joining, we'll show the aliases being joined together and the join keys for that operation. If you're filtering the data, we'll show the filter expression that's actually eliminating data for that filter. So there's some color coding going on here as well. Everywhere in the Lipstick UI, the dark blue represents maps. So logical operators that have a dark blue header are occurring on the map side of a job. logical operations that have an orange header are occurring on the reduce side of the job. And similarly, if the job had currently been running, the MapReduce jobs that are currently executing flash either blue or orange to indicate that they're either in the map phase or the reduce phase. So something else pretty cool that's happening here is you can see we're annotating row counts in the UI. And so anywhere we're loading data, storing data, or materializing data in between MapReduce jobs, we're printing out a count of the rows that we've seen so far. So if the job had been currently running, that would have been updating, as the execution progressed. Here, the job is finished, and so it's the number of rows that were materialized along the script. So zooming back out a bit, if you had clicked on one of those light blue bounding boxes that represent a MapReduce job, we'll change the right-hand side to display some more information that we know about the job. And so, some of the stuff we display are the aliases that constitute the operations inside of the MapReduce job, the number of mappers and reducers that executed as part of it, and the percentage progress made through the map and reduce phase for that MapReduce job. And also all of the counters that we get from the MapReduce framework we display over on the right-hand drawer.
So while I was writing this, I was doing this really quickly, and first thing that I hit was my job started. Well, Pig said my job started, but didn't really do anything. It didn't go to the job tracker. So what would I look at as a user to figure that out?
So this is a close-up of the first job that executes in this color recommendation script. And it's not super exciting. We can see the blue headers indicate that it's map only. There's no orange operations in here. And all it's doing is loading data and running a for each loop against it. So it's probably transforming the data that it loaded somehow. And so, just by looking at it, everything seems pretty legit. I don't see anything going obviously wrong with this view. But one of the more advanced features of the Lipstick UI is the ability to switch in between an optimized view of your logical query plan and an unoptimized view. And so Pig actually has a large series of optimizations it performs on your code in order to make it run as efficiently as possible. And sometimes, or usually, it's useful to see the view of that execution at that optimized level, which is what Pig is actually doing. But to diagnose a certain class of problems, it's helpful to switch over to the unoptimized view of your code. And so in this case, when I switch over to the unoptimized view, I see another logical operation in my graph, and it's colored red. And what red means is that we couldn't map it either to the map side or the reduce side of a job. And the reason for that is this operation is the victim of one of the simplest optimizations that Pig can perform, which is to remove dead code from your script. And so in this case, this filter statement, which was meant to eliminate data that occurred before May 1st, was connected to the load, but then the for each that should have been connected to that filter was actually connected to the original load statement. So the filter has a source but no sink, and Pig realizes that you're not doing anything with that data, why perform the optimization, and it just eliminates it from the graph. So what's actually happening here is rather than loading a couple months of data, this graph is loading all of our view history from the beginning of time at Netflix, and you can imagine that's quite a bit of data. And so the Pig script is just taking a good bit of time to start up.
So I wish I could say that I did this on purpose for this talk, but the second thing that happened was I put in a filter for my own username at the end of this because I wanted to get the just my color vector out of it, and I really didn't get anything out. 0 records came out. So what do I look at there?
So here's a close-up of kind of the middle part of this script. And we can see up at the top here, it's doing a join on a couple pretty big data sets. 100 million rows are being joined with somewhere around 30 to 40 million rows. And so the output of that first MapReduce job only produced 30,000 rows as output. And you can imagine when you're trying to join 100 million rows with tens of millions of rows, you would hope that you would get more than 30,000 rows of output. And so something is clearly wrong here. And another advanced feature of the Lipstick UI is the ability to click on one of those intermediate counters for output and obtain a sampling of the data that's being materialized in between jobs. So if we do that, we can see what's actually going on here is we're joining movie IDs with subscriber IDs, and it looks like there was some overlap in that space, but clearly we can see the join key is wrong, and it's something that's now easy to fix.
So maybe I'll just explain this one. So which is, my job failed, and what happened is, now in the interface I can see in context where it failed, really quickly, look at the data that came into it, and really, there's not much going on here. It turned out that I had a UDF that was failing, so after I fixed, my join, I could go back and in here click through to the job tracker and figure out what failed. So it's really nice to see your errors in context. Once I got that all done, here's what came out. It thinks I should watch Power Rangers, and Jeff should watch some things which I'm pretty sure that he's not going to enjoy. And really quickly to explain what happened here is we were averaging titles, and what happens is, unless people are watching a clustered, colors, they get projected into the average space of the entire set of titles, and these are the titles that are closest to that middle. So we decided not to push this to production, so you won't be seeing this on your page.
So even though our recommendation engine didn't work out today, we hope that we showed you some of the cool tools that we're building on top of our data platform as a service. And unfortunately, during this talk, we've been limited to screenshots on PowerPoint slides. And we feel that all of these tools are actually a lot more interesting if you can play with them in person. And so Charles and I are going to be at the Netflix booth in the exhibit hall for the next couple of hours until it closes. And we're more than happy to show you demos of Lipstick, Sting, and Genie running in our production environment and let you click around and play with the tools and actually see them flashing and graphing in sub-second, whatever. So another announcement that we made yesterday is that Lipstick is part of Netflix open source. So feel free to clone it on GitHub. Genie is the same. So we open sourced that last week, and the link to that is very similar. It's Netflix/Genie. We'd also like to mention that we're holding a new Netflix OSS Cloud Prize. And so if anybody is so inclined to contribute to these pieces of software, you might be able to win something by doing it as well. But regardless, we'd love to hear your feedback on the tools. We'd be more than happy to help you set them up and work with them in your environment. So definitely come by and talk to us, and maybe get a cool piece of Lipstick swag, which is chapstick. So thanks again for coming to our talk today, and we're more than happy to answer questions in the time we have left.
Great presentation. I just had a quick question on your Franklin layer. Could you disambiguate that from, like, say, hcatalog?
Do I get to take it? So yeah, we started this around the same time that hcatalog was incubating, and there's two things why we use Franklin instead of hcatalog. So they provide a very similar functionality for us, but one is we want to back into a lot of different metadata stores. So like as we mentioned, some of it's Hive, and that's that's great. That's like hcatalog. But we also have multiple Hive meta stores. We also have Teradata and MySQL, and so we just wanted to have a way to do that. And another feature that we use, which is one of the other reasons that we didn't delve more into hcatalog, is we often restate partitions, and we want to store into partitions that already exist without deleting them. And so we've implemented this batch pattern that is not really compatible with hcatalog. So it's very similar in some ways, but in other ways, for us, it's just a simple REST interface that we can go across all our data at once.
Cool, thank you.
So if I recall correctly, right, the metadata API was called Frankie or Franklin?
Franklin.
Franklin, okay. So did you folks have to actually have the developers actually log into Franklin each time they push data in during ingestion, or how did you all make
So,
that happen?
so Franklin sits on top of other meta stores. So, like as data goes into Hive, it's available in Franklin, or as it's in your MySQL database, it's in Franklin. So when you're storing data, you store it to a name, Franklin knows about it, and it updates the meta stores appropriately, for that data.
Thanks.
Hello. I'm very insisting about the lipstick. Yeah. I have two questions. When the pig become complicated, so this graph will become very large, right?
Yes. The graph will be large if it's complicated.
Okay. That way maybe will be a problem. Maybe to complete the graph.
So the interface actually allows users to zoom in and out and kind of, manipulate their way around that picture. And so, certainly when it's large, it's hard to see the whole thing at once. We'll display it very small, right? But you can zoom into individual pieces of that and take a larger look at what's going on.
Okay. So how did you get the record count after each step?
I missed that one.
So I see you.
How do we get the record count?
Yeah.
We're using the Pig process notification listener, and we're getting stats back from the job tracker. We're pushing that back to the server, and we're using D3 to display that on the graph. And we'd love to talk about the technical aspect if you want to catch up with us afterwards. If you want to ask any more questions like that, it's a lot easier.
Okay, thank you.
So actually, my question was similar. Was going to ask about how you get the number of records in between jobs and the sample. So I'm assuming you opening the temporary store in between jobs and looking at the first records.
Yes, yeah. So we see the inner storage, and do you want to answer that one a little more?
Yeah, so Pig progress notification listener lets us know when a job is finished. And so we're basically just, looking at that job. It stores data using a class called inner storage. And we're using methods on that class to just open up the data and read the intermediate data from HDFS.
Yeah, about 10 lines.
Okay, and so the stats are coming from Pig. So that comes from the counters of the job?
Yes.
Exactly.
Okay. Thanks.
Hi. So with the lipstick UI, I saw it was showing all the different sort of main pig operators for each group, Will it show all the different UDFs that you had inserted throughout all those different statements? And can you zoom in to see if those were the problem when it fails and all that?
Sure. So one of the things we didn't show is we actually do provide the actual script that ran, right, in another drawer that we just didn't expand on the slides. And one of the cool features of Lipstick is that you can click on any of those logical operations and see where they mapped into your actual script, so you can see what lines of code are responsible for those logical operations. As far as actually seeing the UDFs and being able to determine if those are the source of a problem, if in one statement you're running like 7 UDFs, then we can't really surface that kind of insight. But at least if your job fails, you know what portion of your logic to look into and hopefully be able to debug that better.
Okay, thanks.
Yeah, I got 2 questions for the Lipstick. First one is for Lipstick installation, is a client-side installation, or you have to install on every data nodes?
Client side.
Okay. Second is the Lipstick can run on any Hadoop. You don't need to just open Hadoop, will be fine, right?
Sure. Yeah. So we're actually running on pretty much vanilla Apache Pig 11. And so the one requirement is it does use some code that's in Pig 11 and higher. So if you're running like Pig 9, for example, it won't work. But
Thank you.
I guess.
All right. I think he kind of already touched on my first question, which was kind of what components have to be touched in order to get a working Lipstick instance. And then my other question is, you talked about touching the intermediate data. Do you see any performance hindrance with that? Like, is there any effect on the performance of the Pig jobs that were running before Lipstick versus after?
absolutely not. So we're reading just the first 2,000 bytes out of that intermediate result. And so, it takes pretty much no time at all. And if we were really concerned about performance penalty, we could just launch that off in a separate thread and take things from there. So unfortunately, we're out of time here, and we can't take any more questions. But we're more than happy to answer things offline, and definitely in our booth for the next couple of hours. So come by and see us, please.